Wednesday. And we're turning in a problem set. So we'll start by taking questions that y'all have.
I was wondering if you could go over number 8.
Is that the last one?
Yeah.
Yeah, so with number 8, they give us a stack of spheres that's like infinitely many spheres. And they say that the radius of the nth sphere is 1 over the square root of n. And they're stacked on top of each other, and there's a little figure there. So in part A, they ask how high is this stack? So how do we model the height, like the total height of the stack? Like let's suppose there were 3 spheres, right? Sure, right? I mean, but what would we add? Like if there were just 3, there's a snowman. If there were just 3 spheres, right? Like how would we get that height? Sure, but like what are we adding, I guess? We're going to add those diameters together. So so now of course this just kind of keeps going. So the total height is the infinite series of, we just add the diameters. And what are the diameters?
2 times 1 over root a.
Mm-hmm. So I think we kind of want to figure out what happens to that series. And how can we do that? It is like a P-series. What does a P-series look like?
1 over
Mm-hmm.
to some power.
Right, so a P-series is specifically 1 over n to the p. We have this factor of 2 here. What can we do with that?
Split.
Yeah, we could pull out constant factors. So you can model it as a P-series and then just determine what happens to that height. In part B, they ask us to show that the weight is finite. So they tell us already that the density is 1 Newton per cubic meter. So it has like a density of 1. So if we're finding the weight of all of these, what is it that we really just need to add together? Yeah. The total weight, because the density is 1, the total weight is equal to the total volume. And so we're going to figure out what is the volume of each sphere?
R.
4/3 pi r cubed. I'm with you. So, and then they tell us the radius, right? The radius is 1 over root n. So we kind of just put that in this. 4/3 pi, the radius is 1 over root n cubed. So then you just want to determine what happens to that series. We're supposed to conclude that it converges, I think, because they say to show that the weight is finite. But you just want to be clear about your reasoning and how we know that.
So the first question, we don't have to come up with a figure saying how high it is.
Well, I mean, what happens to that series?
It converges.
Why?
It's a P-series and value of P is less than 5. less than 1.
Okay.
And then, well, when you ask how high up, and like we have to come up with a sum of
That would be hard to do with a P-series. So I think we should just take a look at what the rules are for convergence on a P-series.
You can just say convergence, but you can't really define it.
Somebody find how we determine whether or not a P-series converges.
Oh, it's more than 1.
Yeah. So if P is less than or equal to 1, it diverges. Right? That's in essence saying those terms don't get small fast enough. They don't approach 0 fast enough. The way you get it to approach 0 faster is to make the denominator grow faster, and that happens when the P is strictly greater than 1. So yeah, you actually are not, I mean, you could say how high it is, but it won't be a numerical figure. Other questions?
I did like a bunch of homework, so I have
Uh-huh.
a bunch of questions.
Yep.
The first one is on in 9.1
Yeah.
and number 17. It's n plus 1 factorial over n minus 1 factorial.
Like this. And that's just the nth term in the sequence.
Right.
And they want us to know if it converges or not.
I think there might have been a graph.
Hold on. Give me 1 second. I'm going to log into my thing that lets me, we can actually see the pictures.
I think it was both table. So what did you do that in so modified.
It's from 9.1.
I'm almost there. Okay. All right.
Yeah, they're simplifying.
Oh, just simplify. Yes. Okay. I got you. I want Zoom to stop giving me that message right in the middle of my effing screen. Okay. Thank you. Thanks, Zoom. Okay. So we want to simplify this factorial. How do we do that? Like, what's a way to start? So it's just n plus 1 over n minus 1? No.
I was trying to expand them out.
Okay.
So I have like n plus 1 and then we have like n factorial and n minus 1, but I didn't.
Oh, yeah. So you know what? Let's expand it further. Let's say n plus 1 factorial is n plus 1. The next one down is n. Then the next one down is n minus 1. And then n minus 2. N minus 3. We don't have to necessarily have to go this far, but like it goes all the way down to times 2 times 1, right? This is the same, and then in the bottom, we have n minus 1. The next one down is n minus 2, n minus 3, all the way down. What happens?
Now you can start doing some canceling.
Yeah. Right, like all of these cancel with all of these. In essence, I'm going to rewrite like another way to write this. I mean, at this point we can just say what it is, right? We're going to get n plus 1 times n. That's what we're left with.
Yeah,
But another way to write this, and the way you might see it on CalcChat, is n plus 1 times n minus 1 factorial. Kind of a shorthand of saying like, oh, that's got all the rest of the factors. And then on the bottom, n minus 1 factorial. We chose to write that as n plus 1 n minus 1 factorial instead of n plus 1 times n factorial, precisely because that's what allows us to see what cancels. So now these cancel, and of course we get the same thing.
Okay. Okay. This is from, I think still in 9.1.
Yep.
Number 55.
So monotonic and bounded, determine whether the sequence is monotonic and whether it's bounded. Use the graphing utility to confirm. So in 55 we have n e to the minus n over 2. Okay. And bounded, monotonic and bounded, of course, we're considering values of n1 and greater. I guess if I were looking at this, I might start by just rewriting it. Like, this is the same as n over e to the n over 2. And is it monotonic? So certainly it seems like it would be decreasing. Like the terms definitely approach 0, right? Like exponential growth in the bottom versus linear growth up top. They're going to approach 0. We could see if, in fact, maybe it'll be easier to use this form. Like if we look at the continuous function, we could find the derivative and see if that's always negative. So gf prime would be e to the negative x over 2 times 1 plus fg prime e to the minus x over 2 times a negative 1/2. I'm going to pull out a common factor of e to the minus x over 2. And then we have 1 minus 1/2 x left. So that is 1 minus 1/2 x over e to the x over 2. And we want to know, is that always negative for where x is at least as big as 1? I think we have to wait till we get x equal to 2. When x is 2, it's 0. And then beyond that, it's always negative. I think x equals 1 is, it's the only place it's positive. Because e to the x over 2 on the bottom is always positive, the exponential. So I guess I would say this is less than 1 where x is strictly greater than 2. Or sorry, less than 0. So I'd say, I guess it's monotonic where x is at least as big as 2. If we ignore the first term, then we'd have a monotonic sequence. And then is it bounded? I think it's got to be. The terms approach 0. The terms approach 0, and Oh yeah, I think it's got to be bounded. The terms approach 0, and the terms are always positive. And we showed that it's monotonic as long as n is at least as big as 2. So if we ignore the first term, then it's bounded and monotonic. Like if something's only moving in the downward direction, the terms are only positive, it's only moving in the downward direction and approaching 0, then it has to be bounded, right? There's nothing that makes it blow up because we're not going to be dividing by 0. N itself, like as n gets big, the numerator grows linearly and the denominator grows exponentially. Let's throw this in the calculator.
What made you decide to take the derivative?
Oh, to see if it was decreasing.
Okay.
So, like, if the derivative is negative, that means it's decreasing. And if we can show the derivative is always negative for some set of values, then that means it'll be always decreasing. It's not the only way. Like, sometimes we do it algebraically, and we look at, is a sub n plus 1 less than a sub n?
Okay.
And so is this less than... You know, try to do that out in that fashion. I usually, whether I use like the derivative approach or this more algebraic approach, I just do what seems like it might be the least amount of work or give me results easiest. You know. So let's see. We have x over e to the x over 2. And we're going to look at it from, I guess, 1, I don't know, to 100. And I'll let the y min be 0 and the y max be, I'm going to go 0 to 1 and see what it looks like first. Oh, yeah. So there's that little bit in the beginning where it's increasing. And that's sort of where I said let's just ignore that first term, and then it's decreasing, and it's always, we could sort of see that solid blue line at the bottom. Does that help?
Yep.
Okay.
Yep. And 9.2 number 17.
Oh, verify that it diverges. Okay, so we have 4 to the n plus 3 over 4 raised to the n plus 1 power. If we're going to verify that something diverges, I mean, I guess we have our pick of like lots of different lots of convergence tests, but and for a problem in this section, like this is the first section where we're looking at series, there's not a lot of convergence tests we've looked at, so I'm just going to jump into the nth term test. Remember, the nth term test can only be used to show divergence. You can't conclude anything converges with the nth term test. So we're going to look at the limit as n approaches infinity of the nth term, 4 to the n plus 3 divided by 4 to the n plus 1. So more than one way we could do this. I think I'll multiply, I think I'll try this algebraically. Maybe if we multiply top and bottom by 1 over 4 to the n plus 1. I think that would work. I'm going to do 1 over 4 to the n, though. I think that will be more convenient. So on the bottom, we get 4, right? There's one more factor of 4 on the top than on the bottom, so we get 4 down there. Up top, what do we get?
3. 1 plus 3.
1 plus, if I distribute this,
Oh, no. That'll be 3 over 4 again.
yeah, so this one goes to 0.
4.
So what is this overall limit?
1/4.
1/4. What is it that we want to observe about this?
It's not 0.
Not 0. And that means that the series diverges.
I think 9.4. I think is the one that comes from one. Number 9 and number 11.
9 and 11. Okay. So let's start with 9. Ln n over n plus 1.
I think this is direct.
Yeah, it asks us to use the direct comparison test.
So I was like, oh, compare ln n over n, and it didn't really,
Well, ln n over n, I mean, okay. Let's try that. We need first, so this is going to create a new problem for us. Because ln n over n, it doesn't create a new problem, but like inherent in any comparison test is we need to know what that comparison series does, and we need to be able to show it, right? So I'm trying to think about how we would, so that'd be our first thing. What does this guy do? And my gut tells me that it diverges. My gut is not proof, but like that's where I'm headed with this. So, and this was n equals 2 to infinity. But just looking at its form, I might try to look at this using the integral test. Like if f of x is ln x over x, that is continuous where x is greater than 2, greater than or equal to 2, because we're not going to divide by 0, and the ln just has a problem when, ln blows up between 0 and 1. So like when x is at least as big as 2, like we're in good shape there, it's continuous. Is it decreasing? Yeah, you could show it by taking a derivative, or you could even observe it by looking at the graphs, but ln x grows way slower than x does. And it's always positive where n is at least as big as 2. So I think the integral test will apply. So if we look at the integral from 2 to infinity, ln x over x dx, this is the limit as b approaches infinity, and 2 to b. And I'm going to rewrite this as ln x times 1 over x dx. And I'm writing it that way because we can make a u substitution. Right, if u is ln x, du is 1 over x dx. So this is u du. Right, that's just a power rule integral. The 1/2 u squared. So 1/2 u squared, I'm going to do 2 steps in one if that's okay. I'm going to put the u back in. So u is ln x, so we have 1/2 ln x squared from 2 to b. One half time, pull the 1/2 out, and then we have ln b squared minus ln 2 squared. And ln 2 is a constant, so ln 2 squared is a constant. As b gets huge, ln b gets huge. Slowly, but still gets huge. So ln b squared also gets huge. This limit is infinite. And so that means that this series diverges. Oh, man. Okay. I think I picked a series that's going to make the direct comparison test hard. Oh, wait, no. Wait. Oh, yeah, okay. All right.
Could you have picked like 1 over n to compare?
Yeah, that might be better.
Just around-
The problem is that certainly we found out what happens to the comparison series, and it is reasonable that our series will have the same behavior because they're virtually the same, and as n gets huge, the +1 becomes insignificant. And we could definitely show that using the limit comparison test pretty easy. And if they want us to use the direct comparison test, though, if we're comparing it to something that diverges, we have to show that our terms are greater than something that diverges. These terms of our series are less than the one that diverges. And in that case, the direct comparison test is inconclusive. So Nathan suggests 1 over n. We know that we don't need to do a separate test there. We know that's a divergent P-series. So is ln n over n plus 1 greater than 1 over n? And how would we know? We could. Let's just see. So what if we worked with this inequality? So we got a big question mark here right now, but if we multiply both sides by the LCD just to clear denominators, that would look like n and n plus 1 are both positive because we're looking at n at least as big as 2. So we don't have to worry about having to flip inequalities around. That's a good question. Still a question. I'm going to subtract n. I'm going to play around with this just a little bit. We could factor out the n.
And that was 1 over n.
Oh. We could. Does that make it easier to determine? Oh, probably. Like if you mean like do this?
Yeah.
Yeah. Yeah, for n at least as big as 2, I think that is true. Because, like, ln n just keeps growing. So ln n minus 1 just keeps growing. The other side keeps getting smaller as n gets bigger. I feel pretty confident in saying that that's true. We could take a look on at the graphs on the calculator. So ln x minus 1 versus 1 over m. 1 over x. I'm I'm going to adjust the window just so it goes from 1 to 20 just to get a better view. I'll try that. Oh yeah, so 1, 2, again, I think we have to ignore like the n equals 2 term, but at least it's starting at n equals 3. You can see that ln n one is the increasing one, and this is 1 over n. So I think that is true. And again, when we're making this comparison, like if we can't say that it's true for every single one, but we can say it's true starting at this one and forever after, like that's sufficient. Like if you can show that something is true for your series for all but the first finite number of terms, then that's fine, right? Like figuring out what happens to your series starting at the 10th term onward is the same as figuring out what happens to your series starting at n equals 1. Like you just take what happens to those infinitely many terms and then tack on the finite, whatever finite sum those first ones are. It's not going to change whether it blows up or doesn't blow up if you add a finite number onto it. So this is true for n greater than or equal to 3, which I think allows us to make a conclusion. And so when we're making a conclusion using the direct comparison test, we would say that the terms of this series ln n over n plus 1 are all greater than the terms of a divergent series, which was 1 over n. And that means that our series diverges.
You have to be able to make that comparison.
You need to be, and there. It's possible there could be another series to choose that would be an easier, like, being able to determine that they're greater than. I think we're able to make this work. Like, it's all about like finding a series that you can figure out what happens to and be able to make the comparison. If I were doing this problem and they hadn't asked me to use the direct comparison test, I probably would have picked ln n over n, did what we did here, and then just did the, limit comparison test. Because those ln n factors are going to cancel. And then you just get that limit. I think once you set it up and carry it out, I think that limit is just going to be 1, which is finite and positive. And then you said...
11, yeah, that's...
1 over n factorial.
Right.
Yeah. Direct comparison test. Oh, okay. Yeah, I think this one's going to be easier.
Yeah.
So 9.2, number 11.
I was like, can I compare that with 1 over n? And
well, what do we think happens to the series?
it gets small.
Well, the terms get small, yep. So what happens to the series? Like, do we think they get small fast enough to make it converge? Yeah. So if we're going to use the direct comparison test, I mean, factorial growth is crazy fast. So, I mean, my gut tells me the same thing. But if we're going to use the direct comparison test, if we could develop kind of a gut sense of what this series does, that'll help us pick a series. I'm not going to pick 1 over n, because 1 over n diverges, right? Like, so what we could pick is something that converges, maybe 1 over n squared. Still a p-series, still no work to show that converges, just convergent p-series, right? P is bigger than 1.
So you're choosing exponential to replace the factorial.
I'm choosing polynomial to replace. Like, exponential would be like 2 to the n.
Okay.
Which, you know what, by the way, that would be another one. Or 1 over 2 to the n, which is the same as 1/2 to the n. That's convergent geometric series. I think either of these would be fine. We did the 1 over n factorial less than 1 over 2 to the n. We showed this in class. That was like we spent a while showing that in class just so we could use that as a fact. You know, we said let's look it out to n at least as big as 4. We showed that as long as n was at least as big as 4, like that was going to be smaller. And we even went further and said that as n gets bigger, we keep tacking on bigger and bigger factors onto the n factorial, but just the same factor onto the other side, and so like that. In fact, it approaches 0 faster. The other one, like this is 1 over n, n minus 1, n minus 2. N times n. So we have yeah. So I think it's better to leave it as n squared because oops. Because where n is at least as big as 2, then this ends up being like n squared. Maybe it ends up being about as the same amount of work.
Open the old slide.
What's that?
Open the old slide, as we already did this one in class.
Oh, we did this one in class. So I was trying to see like doing it for the other series. Yeah. But yeah, we could open the old slide like that would certainly explain this one. I'm just trying to think like maybe you'd want to do it like the same way, like look at the first few terms, see where that's true the first time, and then make the argument that it has to be true.
But if we look at it either with the geometric or the P-series, then we can just say, okay, based on those rules, this series.
Yeah, I mean, I think it's easiest to do it with the geometric one because we established that already in class. With this one, maybe even we could multiply both sides by n first to clear that and get rid of one of those. Oh, you know what? Let's do another factor of n. So this ends up being is n over n minus 1, n minus 2, blah, 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 2 times 1, less than 1. And, yeah, it definitely is.
Right.
Yep.
I think I have number 23.
Same section?
Yeah, it's been 9.4.
Yeah, so 1 over n root n squared plus 1. Here they're asking us to use a limit comparison test. So when we pick a comparison series for the limit comparison test, usually what we do is just ignore all but like the highest powers that appear. So like we have a factor of n in the bottom, obviously, but then that square root of n squared plus 1. Like the plus 1 we imagine is insignificant as n gets huge. So that whole radical, we could treat that as adding just like another factor of n in the bottom, right? Like think of it as a square root of n squared. So I would compare that to,
It shows 1 over n squared.
yeah, nice. And then we take the ratio of the two series, so maybe like 1 over n squared times the reciprocal. And it doesn't matter which way you go. Like with the limit comparison test, either one could be on top or the bottom. We can cancel one of these factors of n right away. Oh, you just have it back. Yeah, so that's fine. So I've got to go in the other way, and there's more than one way you could do this, but that n, that factor of n, is the same as having a square root of n squared.
Right.
And then we could rewrite this as a single radical. And then if you, so because of the way I have mine set up, I could split it up over addition up top. You can't split it up over addition in the bottom. But even if you had it flipped, then you could multiply top and bottom of that fraction by 1 over n squared, like take this approach. And then we get, what, 1 plus 1 over n squared over 1? What's that limit? One. Yep. And what is it when we use the limit comparison test? What is it that we want to observe about that result? Finite and positive. And you want to be explicit about that. Like, you're going to have that list of convergence tests, but like I want to see you making that connection that like this is what it needs to be true. Here it is. I'm specifically citing that result, and that's how I know. And then I'm stating a conclusion. Right? What is our conclusion in this case? Like we picked a comparison test, we ran the limit. What haven't we done yet? Yeah. So what does it do? Why converge? It doesn't converge to 1. I doubt. I agree that it converges. Why?
Is that because of the P-Series?
Yeah, what does this do?
The P-Series Converges?
Yeah, because P is greater than 1. Whenever we're doing a comparison test, we have to say what our comparison series does. Sometimes that requires work. In this case, and that's what's really nice about the limit comparison test, is a lot of times you just compare to a P-series and there's no work to show that. Right? This is a convergent P-series. And the way the limit comparison test works is that if it's finite and positive, then your series does the same thing that your comparison series does. So our series converges.
Okay. And I just have one more.
Mm-hmm.
33.
Same section?
Yeah.
Oh, so determine convergence or divergence using one of these tests. Well, we're not going to do all of them, but we're just going to find one that will work. So this series is n over n squared plus 1 squared. What kind of limit?
b goes to infinity, 1 to b, x over x squared plus 1.
Are you mean, so what test are you using?
I think, the integral test.
Okay, yep. So if we're using the integral test, okay, yeah, that could work. So you're saying let's let f of x equal x over x squared plus 1 squared. It is continuous.
Yeah.
It is definitely positive if x is at least 1. And I'm going to go ahead and say it looks like it's decreasing because I've got linear growth on top and I've got a quartic, like degree 4 polynomial on the bottom. So we're integrating from 1 to infinity x over x squared plus 1. That's a limit as b approaches infinity. Integral from 1 to b. And, oh, that was squared on the bottom. So we've got x squared plus 1 squared to the negative 2 times x dx. How do we approach that integral?
I used u as x squared plus 1.
Great.
And du is 2x dx.
Great.
So I put a 1/2 out in front.
Yeah, so we throw a 2 in here and then a 1/2. And now it's
U goes over 2 du.
and so that's a minus 1 over u when you integrate it.
Yeah.
So,
And, 1/2.
oh, I lost the 1/2, yeah. So 1/2.
Negative, or u is negative 1 over negative 1.
Mm-hmm.
It gave me a quarter as the final. Was it converges to a quarter? I had a half.
So this, let's see, this is minus 1 over u. I'm going to throw the x's back in, so that's minus 1 over x squared plus 1 from 1 to b. Does that look right?
Yeah.
Hold on, I'm going to come over here. Limit b approaches infinity 1/2 times. So now we end up with a negative 1 over b squared plus 1 minus a negative, so plus 1 over 2. Okay. Yeah, we'll get a quarter. Like if as b goes to infinity, this goes to 0. Yeah, so that goes to a half, but then we have this factor of a half here, and we get 1/4. So, what does that mean?
I had P-Series Converges
Yeah.
to a half.
No, it doesn't. We don't know what it converges to. Like, that's really important. The improper integral converges to a quarter. That means that the series converges to we don't know what. They don't converge necessarily to the same thing, but they will have the same general behavior. So, the series converges, we don't know to what.
Yeah, I think I messed up I had like a half times 0 and then negative a half times 1 over 1. So I did.
Okay. Do you want me to scroll back up?
Oh, I see what I did. I think I said the x squared plus 1 was like 1, but it was half. So what?
Oh, I see what you're saying. Yeah. Yep. Other questions? Other problem set questions?
I did number 7, so I just wanted to double check it with you.
Yep. How did you do it?
I was just stuck with it and getting out the big R and integral of temporary things. What I did was
Oh, whoops. It's not a series yet. We're making a series for the function. This one. And then they say centered at c equals 3. And where did you get stuck?
So I got my series,
Mhm.
which was 4/9 on the numerator and bottom 1 minus. That's
Wait.
the divided by.
Oh, 4 over like this?
No, 4/9 divided by. I have got
Oh, I see.
1 minus. Open parentheses. Minus. Open parentheses again. 1/3 x. Minus 1.
Okay. Like that?
Yep.
Okay.
Now I know my A is 4/9 and my R is.
How do you know that that was centered at 3?
Because initially I replaced x with x minus 3,
Okay.
and that's where I got from there.
Right. I'm just saying it's kind of hard to tell in that form, right? Yeah.
But yeah, that's what I did.
You just replaced x with x minus 3.
And you should have like a multiple of 3 on the outside of that negative sign. That would give you x minus 3.
Right. I think maybe what you're referring to is if you factor that out. Like, pull that out, and then you'll see the x minus 3 show up. And that's kind of important. Like, it's hard to tell in a series when you write out a series that it's centered at 3 if you don't see that, like, x minus 3 in parentheses. So, I mean, I think that I would recommend kind of rewriting it in a way that it seems obvious when you write the series that it's centered at 3. Because you see that you have x minus 3 or, in parentheses or multiple, right, for your value of r. You said you just replaced x with x minus 3. If you do that, though, those fractions aren't equal, though, right?
No.
So how do you make them equal?
I have no.
Yeah, right. Okay, so like when you just replace x with x minus 3, that's the same as subtracting 9 in the bottom. Then we can undo that by adding 9, and then you do all that algebra. So then you said you got hung up where?
I got to that point after simplifying it, which probably I need to rewrite.
So I think that works, right? Like, because then that's a negative 1/3 x plus 1. That works. And then continue.
I have my A as 4/9,
Mm-hmm.
and my R is 1/3 times x minus 3.
And then what do we do?
Now we set it less than 1, is that right?
Yeah, so what we get convergence when absolute r is less than 1, so we're going to have absolute negative 1/3 less than 1.
But why do we do less than 1?
Why do we do less than
Why do
1?
we assume it's less than 1?
Oh, we don't. We just set it less than 1. We're finding where it
Okay.
converges,
Okay.
right? In order to have convergence, that has to be less than 1. So we're finding the values of x that make that true. We're not assuming that in fact, it's not always less than 1. We're going to have some range of values for which that's true,
Okay.
and a range of values. That's how we help find the interval of convergence. Does that make sense?
Yeah, I got 0 and 6 for interval of convergence. Now
Are
this
those the endpoints
Or what the endpoints?
when you're doing that out? You have a lower value and upper value. Are those the endpoints?
I don't know what the endpoints, which endpoints you're referring to. Like, what are the lower value and upper value that you see?
Well, like you said, 0 and 6. Just looking out. How you get that out.
Right, so I'm just saying there's probably some algebra to do,
Yeah, yeah, yeah.
right?
And
Okay.
you have to get rid of the 1/3. And
Yeah.
add the 3.
So if we multiply by 3, then we have absolute x minus 3 is less than 3.
I got 4/8.
It's something wrong.
So we have some disagreement about what the value of a needs to be. So you added 2 and 9, right? That makes 11 here. And yeah, it looks like in order to make that a 1, you probably have to multiply by 1/11. So there's some dispute about this value. So think about what we do to get it in the 1 minus r form in the bottom. What do you multiply in the top and the bottom? Does that answer your question mostly, or do you still have a question? Like, is there...
So,
So, like, the big R, like, once you, like, if we look at this part here, right? Because the coefficient on x in the absolute values is 1, then whatever the value is over here, like, that's our radius, right? This tells us the big R is equal to 3. And it's centered at 3, so we can go 3 in either direction and get the interval of convergence that way. Another way to look at it is that if absolute value of x minus 3 is less than 3, that means that whatever x minus 3 is has to be between -3 and 3. If its absolute value is less than 3, then remove the absolute value. That has to be between -3 and 3. So that would allow us to set up a 3-sided inequality. And then you could add 3 to all 3 sides. Yep. Yep.
On number 2,
Mm-hmm.
when I saw you earlier, I did the problem like a different way.
Yep.
And so this time instead of comparing with like 1/4 n, I just did 1/n.
Yep.
And I was like, oh, well, that's a P-series.
Mm-hmm.
And then I can just say, convergent.
Well, once you, so if you're, what comparison did you make?
I compared 1/.
Right. So you tell me so you've identified your comparison series.
Yeah.
You said that you're doing 1/4n plus 1 versus 1/n, and you said that this is a P-series that diverges, which is correct. And you said then it converges. Why? What's the
No, I didn't
comparison?
say then it-
Or sorry, then it diverges.
right.
But what's?
I still need to do the comparison.
Yeah. Yeah.
Yeah.
Yep.
I realize that now after doing all this review.
Mhm.
I didn't quite realize that.
And one of the comparison tests will lead to frustration, and one of the comparison tests will lead to victory.
Okay. All right.
Other questions? Okay. Questions from anybody else? All right.
Can I get a card? Do you have any more of those cards?
I think I have some in my office, so if you have a few minutes, you could follow me back. So you've successfully prevented us from starting new material yet. Like, perfect. This is like, I take whatever time you want to cover questions. We're gonna start this packet, so please bring it back with you on Friday. We'll start this packet on Friday. I imagine we'll probably be done with new material by Wednesday, which means we'll have at least the Monday of that last day of classes, Monday, maybe Friday and Monday, to spend working on like covering questions. There'll be a practice final exam that I'll have available probably the end of this week. Have it posted. Nope, there's no problem set.
The test on Wednesday,
Yep.
is that similar to the problem set, would you say, or?
I mean, it's similar in that you're gonna have some. Yeah, there's gonna be some infinite series. There's gonna be some questions where you're given a series and just determine whether it
Similar
converges.
material, that's what I mean.
Yeah, it's this chapter. Yeah, some series you'll be given. There's gonna be some questions where you determine convergence or divergence of a given series. Some where you're gonna find a power series, a geometric power series, or maybe something that's not on this problem set. There's not like, you find a Taylor polynomial, but there's not one that says like find a Taylor series, like infinite series, or how we obtain one series from another series, like using a function composition, like so it's going to be somewhat similar, but definitely do not rely solely on the problem set to prepare yourself for the test. Right? You should look at the exercises and the examples that we've done in class.